My name is Ahmed Ramahi, and I'll be presenting our research titled Aerodynamic Optimization of a Hybrid Vertical Axis Wind Turbine Using Dimples as Passive Flow Control. As we look towards the future, sustainability has become a fundamental goal for many nations and countries. The UAE in specific has an energy strategy by 2050 that aims to increase the contribution of renewable energy to 44% of the country's total energy mix, reducing their reliance on fossil fuels and thus ensuring long-term energy security. However, wind energy remains underutilized in the Gulf region due to the relatively low and inconsistent wind speeds that are available, and currently it is making it imperative to develop optimized and efficient turbine designs that can function in such conditions. The current aspect and the current research focus that is available in terms of renewable energy within the Gulf and the UAE in general is to optimize the use of solar panels and use thermal energy in order to be part of the renewable energy systems. However, this research will be tackling the advancements of wind energy and how we can later on integrate and contribute to a different type and an additional type of renewable energy sources within the Gulf and the UAE in general. So the transition to renewable energy is currently more critical than ever, as fossil fuel dependency continues to contribute to climate changes and environmental degradation. Wind energy is a key player in this transition, offering a sustainable and a cost-effective alternative. This research will aim to enhance the aerodynamic efficiency of vertical axis wind turbines using passive flow controls techniques, and specifically dimples. There have been extensive studies that have optimized horizontal axis wind turbine studies, and limited research exists on improving the vertical axis wind turbines, and this research will focus on allowing us to have a hybrid vertical axis in addition to passive flow control techniques that would allow us to further enhance the aerodynamic efficiency and alter with the flow operation around the turbines. Now, with these objectives in mind, let's currently dig in and explore the fundamentals of wind energy and what are the different types that are available in the market. So wind turbines in general can be divided into two main categories. First is the horizontal axis, which is widely used, has extensive research on, and currently used in a lot of European countries as well. And we have the vertical axis wind turbines that are available as well. So vertical axis is divided into three different types. It could be a drag-based turbine, a lift-based turbine, and a hybrid-based turbine. Let me dig into the advantages and disadvantages of each quickly. So for the Savonius-based, it is considered to be a drag-based turbine where it can operate efficiently at low wind speeds, which is what we currently need, and it has a simple construction and ease of maintenance. However, it has a lower efficiency due to the high forces that are available. The lift-based, which are the Darius turbines, they can be more efficient than Savonius turbines due to their lift-based operation rather than having them as a drag-based, and they have higher rotational speed with a better energy conversion. However, they require an external force, such as a motor, for their self-starting capability. And finally, we have the hybrid, which combines the best and the better of both types and tries to limit the disadvantages that are available within both types. So before going ahead with the research, thorough literature was conducted in terms of understanding the different shapes and different types of dimples that could be added. What pattern do we go ahead and add on the turbine? What shape of dimples do we add? Is there any specific diameter to depth ratio? Multiple patterns were analyzed in studies such as aligned, randomized, and staggered. Multiple shapes were also studied, such as the circular dimples, square dimples, and diamond dimples. And in terms of diameter to depth, an inversely proportional or proportional ratio, let's call it, was analyzed and studied in order to tackle the best diameter to depth ratio for a dimple in the manufacturing process of the turbine. As we further analyzed the literature review, we came ahead and understood that dimples have an effect on flow separation as they go ahead and delay the flow separation and thus improving the boundary layer attachment. In addition to that, we got to know that adding dimples on the surface of the blades would further improve the lift-to-drag ratio. The dimples shape optimization, where different patterns, different shapes were analyzed, was also conducted in the literature review, and other passive flow control methods other than the dimples were analyzed, such as vortex generators and turbulators as well. Two different conceptual designs were conducted and were performed using Fusion 360. First is a hybrid vertical axis wind turbine available in Figure 2, and Figure 3 shows a helical vertical axis wind turbine, both having dimples incorporated on the surface of the blades. A specific decision matrix was analyzed under the criteria of efficiency, cost, structural complexity, environmental impact, and the self-starting capability, and weighted depending on the criteria that is specified. A clear winner of the hybrid vertical axis wind turbine was chosen as per the decision matrix. And to keep it in mind, a 3D printed model of the helical vertical axis wind turbine was kept to be stored at the office. So to move on, the design overview of the chosen hybrid vertical axis wind turbine is as illustrated in the table, and as an additional an additional study that was conducted, we were keen to understand the difference and the connection between the height of the turbine and the width of the turbine, and how could it further enhance the understanding of the power generation. And thus, the actual design over here is a telescopic shaft, allowing us to have adjustable blades in terms of vertical height and horizontal width as well. So the vertical height of the turbine extends from 500 millimeters up to 1,000 millimeters. And in terms of the vertical, they extend from 1,500 millimeters to 2,500 millimeters. And thus, the maximum height the turbine can reach is 2.5 meters. And the lowest height that the turbine could be at is 1.5 meters. To further improve the efficiency of the turbine as well, a mechanical pulley system with a ratio of 5:1 was placed inside the mast labeled F, which allows us to have 5 rotations within the generator at every 1 full rotation of the turbine. This is the design overview of the actual dimples, where after further analysis from the literature review, we came to a realization that a perfect dimple ratio, which is the depth over the diameter of 0.4, has the highest impact on the aerodynamic efficiency of the turbine. In addition, a staggered pattern with a round-shaped dimple was the chosen based on the studies that were conducted from the literature. To take you ahead with our manufacturing process, we start from the left side of the slides, where you can see different vertical shafts and horizontal shafts that are stacked together, the connections between the shafts and the mast, and how the double bearing system was applied. In addition, later on, we started manufacturing the dimple one by one in order to get the actual size and the actual shape. And then lastly, the connections of the Darius blade with the shaft came to a realization in order to give us the final model, which looks like this. It is a built-on model and it's available within the campus. So the final model consists of 4 different Darius blades with aluminum as the chosen material, 2 different Savonius blades with also aluminum as the chosen material. The braid airfoil is an NACA 0015, which contributes to 1.5 millimeter thickness for the blades. The base is made up of mild steel in order to have the structural integrity of the turbine and to keep it placed on the floor as well. And the telescopic shafts are made of aluminum. For the methodology and the results of the power generation experimental testing, which is the first method that was conducted in the research, this was the experimental setup for the power generation, in which we had our Arduino setup with a sensor that would detect the voltage and the current that is directly connected to the generator. In order to dig deeper into what it actually had, the Arduino model connected to 2 different sensors. One is the voltage and current sensor, in which it extracted readings from the generator, and another sensor, which is the Hall effect sensor that detected how many rotations are actually occurring within the turbine itself. And the Arduino was incorporated with another SD card module so that it keeps on recording and storing the data whenever we have. And in order to calculate the instantaneous power that is available, the voltage from the reading multiplied by the current from the reading was done in a formulation in order to have the instantaneous power that is available at every second. In addition to that, a 100 ohm resistor was acted to act as a dummy load in order to have a flow internally within the circuit. For the power generation experimental setup, to move on as well, a Darius angle of attack study was conducted in order to understand at what position do we go ahead and place our Darius angle of attack? Do we keep it at steady at a 0 angle? Do we further increase? If we increase, what does that affect and how effective it could actually be? So a specific study at changing and altering with the angle of attack of the Darius blade at every 10 degrees was conducted, and we found that the optimal, as shown in red, was between angles of 30 and 40 degrees, allowing us to achieve a rotation, 8 rotations per minute, thus reflecting to 40 rotations per minute within the generator due to the impact of the pulley system that was added. So as explained previously, we have an adjustable adjustable height and adjustable width for the turbine. So 15 different analyses and 15 different studies were conducted. And it is shown to have the best model at vertical height of 2.5 meters, along with a horizontal width of 1 meter, achieving 7.4 kilowatts per day. And as shown, we have a steady increase of approximately 20% at each increase in height. To further move on, the coefficient of power was also incorporated over here and achieved a value of 0.275. The coefficient of performance achieved a value of 0.275, which correlates to the maximum Betz limit, theoretical Betz limit of the maximum efficiency that the vertical axis wind turbine can reach is 0.593. For the second part of our methodology, we went ahead with the smoke visualization in order to understand and analyze further and further the enhancement of the aerodynamic performance on the turbine. So a piping system was manufactured in order to ensure smooth laminar flows after at hitting each blade. And over here, this is a dimpled versus undimpled surface. To further analyze, as shown, for the dimpled blade, the flow separation is delayed and it occurs further down the stream, as seen in the yellow arrow in the left image, where the smoke remains attached to the dimples. This is suggesting that the dimples are helping re-energize the flow. In addition to that, we have localized turbulence over the dimpled blade, and in contrast, the smooth blade exhibits some broad, chaotic, and turbulence in the wake. And overall, the dimpled blade exhibits superior aerodynamic efficiency by reducing the drag, enhancing the lift, and controlling the flow separation. And as shown in terms of the undimpled surface or the smooth surface, you have broad and the chaotic behavior within the flow, the smoke flow. The levelized cost of energy was analyzed, which is a critical metric in evaluating the economic viability of renewable energy systems. It represents basically the per unit cost of electricity over the lifetime of a project, considering all the capital, operational, and the maintenance expenses. So it was analyzed to have it as 0.203 dirhams per kilowatt hour, and contributing and correlating this to the United Arab Emirates average grid electricity cost, which is 0.3. This results in a reduction in that, and thus over the long run, it is economically feasible. So in conclusion, this project aimed to analyze a hybrid vertical axis wind turbine that was designed with innovative features, including dimpled blades with a 0.4 dimple ratio. The turbine has an adjustability in height, in addition to a mechanical pulley system that allows for further generation of energy within the generator. And the experimental results demonstrated that the turbine's overall optimal performance is at 2.5 meters in height and 1 meter in width, achieving 7.4 kilowatt hours per day, and thus validating its efficiency. This research has explored the effect of adding dimples on the surface of a variable height swept area hybrid vertical axis wind turbine, and has achieved a 0.273 coefficient of performance with a 0.203 dirhams per kilowatt hour cost. Thank you very much, and I hope you enjoyed the presentation.